theory in cosmology, Elizabeth.
Thank you very much. Good to be here. I'm enjoying the conference very much. Like everybody else, I'm trying to figure out what the nature of reality is. And this talk is on the cosmos, so it's sort of big, so I didn't include my consciousness so much in it as a formulation. But yes, I agree with the last speaker. You have to take in the nature of your own perception to understand what you're really observing, and the fact that there's many states of observations. I worked on this model at Lawrence Berkeley National Laboratory for a number of years, and I worked with, go back, some of the current work I'm doing with JJ and Desiree Hurtak of the Academy for Future Science, which means it doesn't exist in the now, but it will exist in the future, so that's about time machines. And they've been very helpful in some of my current research. Our theory is based on 5 propositions which unify to attempt to unify the branches of physics in the 4 force fields. A fundamental role of constancy of the universal constants is very important. And in the multi-universe, people said, well, maybe there are other constants, but you have to be able to detect the other universes to have them be something to consider and real and viable. The fundamental significance of the role I'm taking as canonically conjugate variables comes out of the Hamilton-Jacobi mechanics that led to the quantum theory of abelian and non-abelian algebras. The geometrical interpretation of the space-time manifold in terms of quantities that comprise a multidimensional space. The introduction of new quantized procedure, an introduction of a 10 and 11-dimensional Descartes space. I've also worked with a complex dimensional 8 and 12-dimensional space. But this is actually real dimensions and not rolled up dimensions. And in the multidimensional geometry, I think that's the only approach we can take to get a true attempt at a unified field theory. I use the Planck units and I call them extended dimensions. I had ED, but that's standard for erectile dysfunction, so that's why I put an END to distinguish what I'm doing from Viagra. And of course, there's a standard length, wormhole, time, momentum, and energy. And what's really interesting is this inspired John Wheeler, who inspired me. John Wheeler has been a great friend of mine, and we have sort of converged our paths over the years, and I'm sorry he's no longer with us. Then I make a set of paired variables that are canonically conjugate variables that are Heisenberg-like in that they're non-abelian algebras. So I have a set of these variables that make up, like for instance, whoops, let's see, I'm going the wrong way. So I have space and momentum, of course, which is the standard Heisenberg principle, and time and energy, which is the standard, also a standard but somewhat controversial Heisenberg principle. But I make another set of these, so I come out with 6 because I have momentum and energy, which is also a 4 space. This is a 6 space. This is a 2-dimensional space. This is actually a 4-dimensional space, and this is a 4-dimensional space, which actually is a Minkowski space. We consider one component of each vector for simplicity in our initial model, and then we calculate our 4 new relationships, which are new Heisenberg Abelian algebra canonically conjugate variables, and there's a whole group theory behind this approach. One of these relates to the force, which is in the stress energy tensor of pi c fourth over g. I think it's 2 pi, 1 over 4 pi c fourth over g, and this actually is a force unit. And I think it's a force that expands the universe in the cosmological current model. We consider the components of the vector quantities, as I say, in terms of the force space, and then we can make the usual space-time connection of the Minkowski space in terms of the dimensions of x, y, z, and t. And the universal constant, of course, comes in here, as well as E equals mc squared. So it's interesting the roles that universal constants occupy. Also, I use this metric for the force space, plus, 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 minus for time. The usual definition of a force space invariant is in terms of a spatial quantity or vector or scalar quantity. So you have a vector, for instance here, which would be a 3 vector, and a scalar. So you get a new set of equations which I derive in terms of these different sets of canonically conjugate relationships. And then here's another one in terms of x and e. And so, oops, did I hit x and e, which makes up force space, and then expressed in terms of this stress energy term in Einstein's field equations. The generalized invariant can be written such as this, where we have a matrix relationship that combines all these sets of canonically conjugate variables for the 10-dimensional space. And this is a set of invariant relations, like the invariant of the Minkowski S squared, in terms of a whole set of dimensional pairs, combined with like xt being the usual space-time metric. But also you can have PE, momentum and energy, X and E. And then, and these are, the constants of these are in terms of the velocity of light squared and what I call the force that expands the universe, which is in the stress energy metric. I might call it the Rauscher force, and then everybody can disagree with that, so that would be good. And so we have then a generalized set of Minkowski metrics, which I explained before. Here we formulate the manner in which we solve Einstein's field equation in an n-dimensional Descartes space. I call it a Descartes space because Descartes suggested space and time. But he also said dimensions of energy, momentum, and so forth were dimensions. And in a book on that Einstein wrote the foreword to on republication of Descartes' work, he gave Descartes the credit for him thinking of the Minkowski space, which Minkowski had thought of, but to be interested in that in developing a 4-dimensional space. We've tried to formulate a quantum cosmology, and to be fair, I say try, because we have to try to see whether there's a way of making a self-consistency between the gravitational theory and the quantum mechanics. And I don't know, things like they're discussing the gravitational waves that's been announced in the 60s, and what the facts are for that, I don't know, but it's going to be interesting to see how that plays out.
They still haven't found it.
What?
They still haven't found any gravitational
Oh, well,
waves.
they're claiming they have recently, but I just read the article, and I would say it doesn't meet my criterion, which is meeting the experimentalist and looking at their facility and see how they analyze the data, how they massage the data. So we're trying to find a self-consistency between the Big Bang model, Einstein's field equations, and without Gus' inflationary model. I might as well tell you what I don't believe in. I think the inflationary model is ad hoc. People can ask me questions or give me answers about that at the end of my talk. But it seems too ad hoc. It doesn't make sense to me because I don't see how there's enough energy, there's latent energy to cause the exponential inflation in the early part of the universe. Also, there's an issue about the Big Bang cosmology, and you'll see that I've modified that. The second thing is about multiverses. Multiverses seem to imply to me, like from the Evergram-Wheeler model, that you have to be able to detect them. I can hypothesize anything I want. And in fact, I can hypothesize the moon's made out of cheese, but it isn't. And so it's about observer going off the deep end, because some observers aren't too good. But the point is that unless it's measured, unless I see something that looks like real data, and I'm still shouldn't be a skeptic. I think it's 10 sigma now on the Higgs particle, but I still like to go to CERN and check their data. Actually, dark matter and dark energy, I think, are oxymorons. I think they're real effects like the flat rotational curves for the galaxies, and I also think there may be acceleration at the distant supernovas. But as far as what they mean, because they seem to be labels for something one doesn't understand. Now that might be a first step, but you gotta not get mixed up with the label being the reality. Also, now some of the people for distant galactic acceleration have reintroduced the cosmological constant V. Whoops, I hit it too hard. And I don't know, Einstein said that was the worst mistake he ever made. Because of course then Hubble came out with the expanding universe in the redshift model. But there's also blue shifted objects, which were discussed in the 60s and not anymore. So I wonder about that. That's something to be considered. So you can calculate the Hubble's expansion in terms of course, 1 over the age of the universe, however old you think it is. And I predicted when I was working on this initially in the 70s that the universe would be about the age they have now. So that means that probably it's really older than I think, because every time they make a time mark on space and time, it seems to get bigger to what they think is going on. Then you can calculate the given redshift, where lambda is the rest frame, the lambda is the rest frame wavelength. So here's Einstein's field equations, and as I said, you see c squared over g, c fourth over g comes into the equation in front of the stress energy tensor. Of course, this is the Ricci curvature tensor, the gravitational constant, and then I had included the cosmological term, but in general, I have worked without this term and solving the equations, and they seem to come out very well for a closed universe. And so, of course, T mu nu is the Riemann-Christoffel symbol, and you're not supposed to name stuff after yourself, but I didn't know what else to call it. And so next, so then we express the right side of Einstein's field equations. This is just exemplifying what I was saying before. And if there is a small cosmological constant, it could come into a vacuum term, which is like a Dirac vacuum, not exactly a direct vacuum, but it would be like a vacuum that would come in to the stress energy tensor. Now, this vacuum state could have polarizing effects and may explain the 3-degree blackbody radiation curve having polarity, for instance, without introducing gravitational waves. Then, now I'm going to set C equals and G equals 1, which of course is actually criminal, but that's what everybody does, so I'm going to do that too. And then I'm going to say maybe the vacuum can be expressed by using a parameter like Einstein's cosmological constant. And it actually might not be a constant, it might be variable, because one of the keys is if we have an almost flat Riemannian space, how do the galaxies get formed? How do you get the perturbation? And people have talked about that at this conference. How do you get the small perturbative effect that creates galaxy stars and everything else, you know? Because that's really an important issue. I know when I was at Livermore Lab in the 60s, they had computer simulations, and of course they do have better ones now. But it's very interesting because it's almost a hydrodynamic kind of problem to figure out how does matter coalesce in certain regions of space and also these galactic clusters, and whether that's a meaningful concept or not. The vacuum density that we define for the vacuum is lambda over 8 pi, where again we use the cosmological constant to formulate it. In the standard view, the density of the vacuum approaches 0. That is, there is no vacuum density. And the matter density is approximately 10 to the minus 29 grams, which would give just a closed universe. But if you actually calculate the Planck density, it's 10 to the 93 grams per cubic centimeter, enough to blow up the universe a number of times. So actually, if you turn that into energy. So it's obvious that if there is a vacuum effect, if there is a plenum or field of the vacuum, it's clear that it's going to have to be just a very small part of the Planck vacuum density energy phenomena. Then I make this is the group multiplication table that I made up, and it's probably pretty hard to read from there, but I made up multiplication tables for the little m, I, k, and that's what the solution is. Some of this will be in the paper that I'm publishing in the proceedings. The expansion for the Hubble's constant for the now universe gives us a density of 10 to the minus 29 grams. Now that's where the dark matter and dark energy concept got thrown in, because it isn't enough to close the universe, just a closed universe for k equals 1. So where is that energy coming from? Well, I don't really know, but we could come partially out of the vacuum energy because it's so huge. We might be able to turn some of that into actual effect in the physical world, just like vacuum state polarization affects plasma physics and solid state physics, just like it affects virtual states and particle interactions. So it isn't a really way out hypothesis because there's roles for it. Then you can write the density in terms of 3 times the Hubble's expansion, 8 pi g. And then, of course, the velocity over RH is actually the velocity of light. Now, Hubble's constant is about 10 to the minus 18. It's in that order of magnitude, centimeters, seconds per centimeters. And they're refining this number, but it still gives approximately this kind of a density in the universe. So then this is just a set of the Planck units because I got enamored with them and sort of brought them into the religion of physics. And I'm responsible if it turns out it's completely wrong, so you can blame me for that. No lawsuits, please, prefer that. But anyway, this is just a set of the, whoops. Okay, this is just a set of the Planck units. See, when I pushed it, I have to do it with my fingernail. No, I'm still getting. This is just a set of the Planck units and their values. In the early universes in this, this column, if I can put the laser printer out on without going to another slide. And then this is in the present day universe. So this is like an evolution of the universe from cosmogenesis to current universe. It's amazing how much energy density there really is throughout the universe to cause the expansion. But I will tell you some ideas about how I think there's also a continuous creation component, like Sir Arthur Eddington said. Notice, I mean Sir Fred Hoyle. The universe variables, the universe starts at, of course, 10 to the minus 44 seconds for the Planck unit. And then we assume the velocity of light is constant throughout the universe, because if it isn't, it's too complicated to calculate. And therefore, it doesn't really give us the feeling of what's going on. We take the simplest approach first. Then we have the Schwarzschild conditions, of which the mass of the universe is c squared, the radius of the universe divided by 2g, which is 10 to the 55 grams, or 10 to the 80th hadrons. And it has a radius of 10 to the 28 centimeters. This is a graph of where I take the early universe parameters from the Planck units and say it obeys a Schwarzschild condition for a just closed universe, and expand that to the current universe. And actually, there's two ways of calculating the density. So there is non-linearities, which I think may be another way of looking at Gust's model, not at the early universe, but at the later universe. And his idea was to try to explain non-uniformity. But the fact that it's quite uniform, that the uniformity is quite constant, isotropy and uniformity. And, whoops, go back. I think I skipped one. This is a calculation of the evolution of the parameters throughout the universe. And I guess I'm going to be finishing early, so we'll have a lot of good questions. Then, as I say, what I'm really saying is a very interesting statement. The universe currently of 10 to 28 centimeters, 10 to 55 grams, obeys exactly the Schwarzschild condition. But in order to get that universe, there had to be a continuous creation component, as well as the current model, which is just the Big Bang and everything was created in the beginning, and God left town and let it go, and that was an explosion in his lab when he was a chemist. But I think that, in fact, there is a continuous creation component, and that's the only way you can get a consistency between Einstein's field equations and the current data in the universe. Now, obviously, we're frozen at a point in time. If the universe continues to expand, then it would imply that the matter, or the amount of matter in the universe, is going to continue to increase. So that still would be part of the continuous creation model. It appears that we may be able to reconcile the continuous creation of Big Bang cosmologies in what I call our little whimper model, where a rotation in the 10 space yields matter and energy. So it's like a space-time rotation that yields matter and energy as a transform of the canonically conjugate variables. The initial conditions exploded as a mini black hole that got larger, but it always maintained a black hole solution. The black holes, I hypothesized and published a series of papers in the early 70s on black holes as being real physical objects, and now I'm vindicated with the current ideas about the galactic center black holes, stellar black holes, and otherwise. It's been very interesting. Now I have to find out whether I think that they're right about their observations, and see whether I think they're really real. But I think they might be. I mean, I'd be happy. I can go to bed to sleep better thinking maybe they are, but just don't want to get too close to them because I don't want to get spaghettified. So then we have a larger scale black holes and the surrounding plasma field, and I did a scaling law. The one that I did on the evolution of the universe I call a scaling law, but I did another one calculating the size of black holes versus their fundamental frequency of oscillation. So, and the oscillation, whoopsie daisy, their oscillation is augmented by the plasma fields around surrounding the black holes. And it seems to be polarizing the energy vacuum near the black holes. It also has to do with explaining Hawking radiation. And it may, as I say, it may in part explain Hawking radiation, which is, of course, the electron-positron pair virtual photon effect in producing electron-positron pairs in high-energy conditions. It also seems apparent that every aspect of reality depends on every other aspect, and I have to quote my friend Henry Stapp. Every part of the universe depends on every other part. The bootstrap model of elementary particles developed by Jeff Chu, who was on my PhD thesis at Berkeley, is another statement of this proposition. And everything is made out of everything else. And I really think that a lot of us are looking for what we might call Einstein's unified theory or unified field effects in many different ways. And I see a lot of commonality in some of those theories. And of course, that's our striving to take the picture, as the earlier speaker said, from the mind and see how much it matches reality, because there is a feedback. And you can tweak reality by doing experiments, and that's what's so lovely. You can theorize out the yin-yang, which I love, but I love doing experiments too, to see whether I can tweak the universe and find out what it all means. And I have to get the whole thing solved of all the nature of reality in probably the next 25 years, but you know, I can use all the help I can get, so that's my presentation.
Do we have any questions from the audience? I'm sorry, Al first. And then...
If everything depends on everything, what does that say about the Hubble boundary for every point has its own Hubble boundary?
Well,
and they don't all overlap, do they?
well, you see, I also have another theoretical approach where, and I'm intrigued by the non-locality of the EPR Bell's theorem experiment. Now, of course, that's quantum mechanical, so how far can that be taken into a macroscopic approach? But I have a formalism that formulates a relativistic non-locality theory in a complex 8 space. And about the Hubble's boundary, it's very interesting because what really can or cannot get in and out of a black hole, like the event horizon, I think there must be some information that does, because even the Hawking radiation sort of says that breaks down to some point, I think.
Okay, Anton. Anton.
Just a quick question. The whole Big Bang theory and expansion and inflation, etc., is all based on Einstein's field equations, which is just gravity-based. Why is the electromagnetic forces ignored in cosmology?
Oh, very good question. That was the paper I was going to get ready and present, but I didn't get it ready in time. And what it is to expand this 10 space to include electromagnetic canonically conjugate variables. And I've worked that out. So I've got the physics worked out, but I hadn't got it all in the form of a paper and I don't know if Richard will let me submit another paper. But it's on the electromagnetic part of this.
Punchline. What's the punchline of this?
What's the punchline? I think there's just kind of a cool self-consistency in the macroscopic, this is the macroscopic stuff. On the microscopic stuff, I think it also involves a multidimensional geometry. And these are extended dimensions, unlike the standard model with the Kaluza-Klein wrapped up dimensions. And that's true of my quantum mechanics theory with the complex dimensional spaces.
And then,
Yeah. Quick question, on your topic, I assume by cosmogenesis you mean just Big Bang or something different?
I just mean the start of the universe.
Yeah, but I mean, what
But,
is the?
but,
that's not Big Bang?
okay. Okay, there's been a lot of revisiting the Big Bang, and some of that may be my fault for promulgating the Big Bang when I was at Berkeley. I asked myself, this is a very interesting question. In high school, I asked myself, if there is a Big Bang closed cosmology, what's the temperature outside the universe? I don't have an answer, but in a 10-dimensional space, the topology of that space isn't so clear on inner and outer as it is in a regular 3-space, 1-time dimension. But that's the direction I've moved in, although I've modified the Big Bang to include this continuous creation term that Sir Fred Hoyle introduced, and I think he was sadly neglected, and that his work should be revisited. Hoyle and Nolakar.
so,
I got two questions. The first one, you mentioned the blue shift. Okay, what are the implications of that? And second, what of our colleagues here mentioned that the red shift attenuates to 0. Would you agree with that?
Well, there's the gravitational redshift, and there's the velocity redshift. In other words, there's two forms of redshifts. One is actually just from an object moving like a Doppler shift,
Yeah.
and the other one is a shift due to the existence of gravity. So there actually are two forms of redshifts. The blue shifted objects, to me, were a clinker that said there's something wrong with the current models, and my own would be also have to modify to include that. But when they first discovered quasars, they found that some of the quasars appeared to be blue shifted, and they actually thought they were in the atmosphere. The red and blue, some kind of big atmospheric phenomena. But of course, now they think they're distance. But they've dropped this whole blue, I have a whole bunch of papers from the 60s when I was at Berkeley on blue shifted objects. But they never pursued that. But I think I'm also, with my theory, saying this is what I've developed, but I'm also saying where the clinkers are in it. And also the clinkers in the current theory. Because of course, the homogeneity and isotropy of the universe, if I have a continuous creation, I have to have it in such a way that it tends to maintain that uniformity of structure that we know. I mean, it's lumpy, it's a lumpy universe, but it's kind of looks the same whether you look from the South Pole or the North Pole with an equally good telescope or the Hubbles or something. I don't know if I'm answering that or not.
Well, I was wondering what the implication of the blue shift would be.
Well, I would say I actually thought of a very Star Trekian kind of approach, and that was that there would be white holes as well as black holes, and the white holes would be part of the continuous creation. So maybe that process would come out as a blue shifted process, depending on how we're observing it in the cosmos and how it's aimed towards us.
Elizabeth, this isn't exactly on what, but something when one shows these diagrams of the beginning of the universe, you know, with 10 to the minus 10 seconds, what always comes to my mind is if clocks slow down, presumably to zero when the mass gets very high from gravitational shifts, how can we draw and even think about graphs that show?
I don't agree with the graphs. What I say is there's a bunch of big bangs. In other words, there's a whole bunch of, it's not just one big bang, because I can't see how that could produce all this stuff. And I also have in mind as a subjective thing that there seems to be a negentropic principle in which evolution seems to make things more complex, like humans and animals and plants and so forth. They're more complex than a rock. That doesn't take credence away from the rock. But I also feel there must be some part of the universe that is somehow affecting that and coming in to affect that. But the one big bang with the inflation doesn't ring true to me, because I think it's too small, but it is interesting to note that the universe does seem to obey a Schwarzschild condition, but I think there must be a whole bunch of Schwarzschild conditions, and we sort of see that with the black hole observations that are being made. So I don't have that fully reconciled.
So,
I haven't heard many people speak of the gravitational redshift before. They had the choice, I think, back in the 30s to adopt a gravitational theory of the redshift, but there was no evidence that there was any there was no evidence for a gravitational field, and so they chose the Doppler shift. But recently I've found that gravitational shielding occurs from an experiment with the sun and the moon, and with gravitation, and it's just the right amount to reproduce the Hubble redshift. I'm talking about this on Wednesday.
Well, I'm very interested in that because there's some kind of pendulum experiments where you have like a Foucault pendulum,
Yeah.
and they're very regular, but they claim that there's some deviation when there's a solar or a lunar eclipse where you're getting this small gravitational body in front of the sun. They claim it slows down the Foucault pendulum.
It's a possibility. You have to have a very, you're measuring at the level of 1 centimeter, 10 to the minus centimeters per second squared, 1/1000th of the Earth's gravitation.
I know, and I thought, my gosh, I don't know how to measure that.
Well, they are measuring it. They measured it in this particular
But I have seen
experiment.
data on that, and it certainly struck me that that's an important, if that's verifiable, that's a very, very
Well,
important
I've
experiment.
analyzed it, and I've also predicted the amount of absorption by the moon, and I get the same answer.
Wow, yeah, that's interesting.
This is the first time that gravitational shielding has been observed. The authors of the paper that did the work measuring it, they said that they couldn't offer a explanation of the anomalous effects. They expected quite different effects. But
Well,
I've explained
I
why these
hypothesized-
effects occur.
I hypothesized that we got dual polar forces like charge. And I'm wondering why gravity is monopolar, or is it? Because if there's a shielding effect, that would say there's got to be a counter effect of the moon in there, so therefore there's a plus, there's attraction and perhaps repulsion if you have a gravitational
No,
shield.
it's just affecting the gravitation. It's reducing the gravitation. It's only reducing it by 20 times 10 to the minus 6 centimeters per second squared.
Oh, okay. Okay, that sounds like it's an immeasurable.
It's
I mean,
barely
that would be
measurable,
measurable.
barely measurable.
Yeah, that's measurable.
And it's a big experiment too.
Oh, I want to hear about that. That's great.
Well, we'll be hearing about that shortly. So, Albrecht, you've got a question.
You have said the gravitational constant may be constant or maybe not constant.
That's
If the
the point.
gravitational constant would be some way changed with the time, then there must be a process behind which makes it changing. And do you have any idea what such a process is?
Well, I would say this. I think the way it's being used, and for the distant supernova to look like they're speeding up, would mean to me that the gravitational constant has to be a variable, because if I take a Hubble's expansion, it looks pretty good up to here, and then all of a sudden it's going up to here, then I'm thinking it's going to continue to change as the universe keeps evolving. And so therefore, I would say lambda has to change. Now, whether it's a difference in accessing the potential available energy in the vacuum, I don't know. In other words, if that was somehow being activated, I kind of like that approach better than whatever they mean by dark energy.
I have
Yeah,
an answer on that.
good.
When they occurred back in 89, still 98, I did a similar Hubble diagram with the brightest cluster galaxies, and I didn't see the effect. So the effect is, I found that the effect is associated with large bursts of energy, like the GRBs or the supernova. In effect, it creates a square wave. The explosion can be simulated by a square wave, and if you take the Fourier analysis of that square wave, and you have a range of frequencies, and you redshift each single frequency, and then propagate it towards the observer, and at the observer you reconstitute the pulse. The pulse is spread by 1 plus c, and that accounts for the added distance which they saw. I've told the supernova people about this several times, but I never get an answer.
Very interesting, because somehow, okay,
So it's a mistake.
there are two things that I don't know how to explain, is the flat rotation curves. But there are some calculations I've been working on to see whether I can understand that, not as a dark matter problem, but as some relatively known physics. But the dark energy seems to me, I don't know how good those observations are, but I think there's something that, like you're suggesting, that needs to really
Well,
be.
this is exact.
Well,
It's a very strong effect.
It makes sense to me, and I know that the guys don't want to listen.
No.
No, well, I tell you what, I told my students that if they think I'm wrong to mention it, because there's no point being so attached to your illusion that you pointed your made-up vision of the universe. That you can't absorb something new.
Sorry, you want another question?
No, to continue with this question of the constancy of the gravitational constant, I think this has also to do with the question of multiverses, which you also mentioned. The reason behind the assumption of multiversions is, as I understand it, that it's very surprising that the physical constants are just the way as they are, because it's from the scratch very, very improbable that they are as they are to make a stable universe. On the other hand, if the gravitational constant, which is one of these constants, depends on other constants, like the speed of light or other things, and the speed of light depends again on the extension of the universe. All these things can be connected to each other, and then the whole system, all this can be a feedback process, a circular, closed circle process. And if we have this and this process stabilizes itself, then this would be make unnecessary an assumption of multiverses, because then in our universe, all these constants would control themselves to make a stable system. So that is a question behind it.
Yeah, it is a question. So, okay, if I change, like the expansion of the universe, I think it was Dirac in 1931 and 32, published 2 papers, where he said, what if G depended on T? That is, G got weaker, so things expanded. But once you start changing, it gets to be a can of spaghetti, because if you change any constant, you can change it any way. And it seems to me, I kind of believe in a religion, that somehow the constancy of the universal constant is very important to make this universe the way it is. And whether there's other universes with different constants, how do I detect them? Because my measurement and my equipment is based on these constants. It's based on making instrumentation is based on these constants. So if the other universe didn't have T equals 1 over F or something for Fourier analysis, what would I mean, I get to a point where you may not see them and therefore they wouldn't be viable, but it's an open question. Tagamet introduced the multiverse, I guess, and there's a whole bunch of people on that bandwagon with, I will caution hand waving and not too much physics. But if that is a viable theory, it's got to have some content, it's got to have some meat to it.
Yeah, if we believe that there's only one universe, we need some model or some answer to the question why these physical constants are so in the way as they are to make our universe stable.
You're absolutely right.
And that needs an answer.
I don't know the answer to that. I'm getting older, but I wasn't around when the Big Bang occurred, and I didn't watch the process firsthand. But it's an exceedingly interesting concept. The way I kind of look at it is, I'm just trying to model one universe. If you give me an infinite number, how long is that going to take to figure out? So I'm being a little practical. Very good question, very good question. Any more?
Of the constants that we have in the universe, a lot of them are calculated or measured to like 9 significant figures. And I understand gravity is only about 3 significant figures. Does that tell us that we don't know something about gravity?
It tells us that if I say I'm measuring gravity at the surface of the Earth, and I say theoretically all the gravity is condensed to the center of the Earth, that's the whole theory of, using Newton's law of gravitation. And this was freshman mechanics, and I thought, I'm not so sure about that being a viable theory. So it may be the interpretation of how we think we're making that measurement. And I'm not sure, I've always had the question. It seemed to me that if I just project all the matter from a sphere into the center, how true to making a measurement from that concept am I going to be? I don't know, but you got a good point there, very good point. I have a book that I just recently published with Richard, so I got some handouts if people want to pass them around. And it's everything I wanted to know about reality except the rest of it. And that's in the next book. Any I guess we have a few more minutes. Any more answers?
Just a clarification is for my own self. You mentioned that the multiverse possibly has to do with Everett's, but
Graham Wheeler, that was the initial idea, because of course, what they were saying, at each instant, if I have, I'm not gonna go over to the blackboard, but at each instant I have a timeline going on, then I can have all these break-off probabilities. In
Right,
other words,
right.
I have all the probabilities of Schrodinger's cat being dead or alive, which have maybe unequal values, like A psi alive plus B psi dead, but maybe A is larger than B, and then after a long time, B is going to be larger than A. But suppose I had a whole series of those possibilities. The cat levitates, gets out of the cage, and all that. Then some are more probable than others. But the Evergraham Wheeler idea, which Wheeler kind of got out of, said he didn't believe in it, was that all these other possible solutions are realities in a different quantum universe. And that got kind of extrapolated to the macroscopic multi-universe level.
right, but that argument has to do with quantum mechanics and the collapse of the wave function, and Everett didn't want the collapse, so there's these multiple
Yeah,
universe. But that's
yeah.
quite a bit different from the concept that, well, if there's a big bang for us, why wouldn't it bang somewhere else?
I think that it's,
Why
I
wouldn't
think
there be
it's
multiple bangs?
a kind of a historical branch, because I know some of the people that are into the Big Bang, they sort of took it from an Everett Graham Wheeler non-collapsed universe model. So I'm just sort of saying the people I've talked to, that's sort of the train of thought that I got. That's not the only train of thought, I'm sure. I'm sure of that. But anyway.
Okay, if we come to the end of the discussion, thanks very much, Elizabeth.